Okay, I promised another example of the Lisp to Verilog converter, so let's look at that. Starting Emacs again, starting the Lisp environment again, and using quick load to load up L2V. And there we go. And as usual, I'm going to begin by changing to a temporary directory, /tmp /, and then I'm going to switch to that package. There we go. Okay. Now we can create a file up here. I've actually pre-cooked it because you'll see it's quite complicated, but let's have a quick look. tmp /quad osc.lisp. Okay, so this time the functions are significantly more complex, but still quite easy to understand if you're familiar with Lisp at least. Define a Verilog state machine called quad osc. It has no inputs, it has two outputs. Let's just have a look at the argument list for that. We see its inputs, outputs, parameters, and body. So inputs none, outputs sine and cosine, parameters. These are the parameters to this state machine. The parameters are a Lisp argument list, and so you can use optional line key or whatever. This particular package, Lisp to V, uses my engineering reader package, which allows us to write constants and so forth in Lisp as though they were engineering strings. So Lisp knows what -2.5 dBs is, etc. And we can put a comment in the normal Lispy way you do that. Define a bunch of things. The math behind this is perhaps a little bit intimidating. You can read about this. It's basically the setup required to hold a quadrature configuration at a precise amplitude. In other words, if set up in this way, there will be no increase or decrease in amplitude. It kind of makes an unstable direct form 2 design. And so now look, we see the blocking operator mixed with the non-blocking operator. So it simply says that the S variable goes to accumulator shift Z0 by the difference. And you can see all these things are being calculated in the let form here. So the bottom line is, this is more complicated. It's not obvious what's going on, but nevertheless, it's a few lines of Lisp code, and we're going to compile it. So now we can run it. Run the Verilog state machine. The arguments to Verilog state machine are the last one. I'm just going to do nil, which means use the last one that I made. And we'll just hit the button and go. So here we go. And it created something going on here, look. Sine and cosine. Well, it's running a bit fast, as you can see. We can see the quantization there. So let's just go back, for example, and slow it down a bit. Make the frequency not 1/10 of the clock, but make the frequency 1m of the clock. And again, just to be fancy, we can say 1m, 1 milli. Compile again and run again. And now the quadrature oscillator is running slower. Okay, now turn this into Verilog. Make Verilog code. Make Verilog file, sorry, make Verilog file. And make Verilog file wants to know the thing to work on. By default, it'll run on the last thing that you did. Make Verilog file, done. And now run the Verilog state machine, the last one, using the type Icarus. Run that, and there it is again. Now, behind the scenes, how did it achieve all that? Well, it did it by writing the files. Let me just split this screen horizontally, shrink these down a bit. Let me open up here what it wrote, quadosc.v. This is quadosc.v created by the code we just looked at. And you can see that it's telling us the arguments that it used for F and A, etc. And it has ordered the non-blocking assignments down here and the blocking assignments up here and created the math that we need. It also creates the test bench, quadosc.testbench, which is here, and we can see the basic principles involved. Write the LXT file so you can explore this in GTK Wave if you wish. And there you go. All right, so that was a much more complicated example of using the Lisp to Verilog converter. Thank you.